Hi, I'm Rachel Scher, and I'm excited to talk to you about energy, both in physics and in its social context. So, one of the big questions in physics teaching is, why should we be learning science at all? And there are lots of great reasons to do so. One good one is that science education should serve community decision making, especially about key climate relevant activities, which matter to so many of us. So when we're teaching introductory physics, we should teach about power plants, and we should teach about them in their material and social context. I want to introduce you to Plant Sharer, which is not related to me, which is the largest coal-fired power production facility in North America. And here's a big aerial picture of it. Here is a diagram of Plant Sharer that is meant to illustrate how it works. And I'm going to walk you through the different features of this diagram. Uh, Over here in the boiler and coal and turbine part of the plant, chemical energy in the coal transforms into thermal energy by burning. That heats some steam, which transforms into kinetic energy in the steam. That gets transferred from the boiler to the turbine. Some of the kinetic energy in the turbine is transformed to electrical energy through electromagnetic induction, which is then transferred out to the electrical grid. And finally, other kinetic energy is transferred to the cooling system and transformed into thermal energy that heats the surrounding environment. So this is a great way to analyze a power plant, but it's decontextualized. Like many physics analyses, these diagrams represent the physics phenomena as mostly separate from the world around them. And this is an intentional stance. Physics is a discipline that values universality and is purposely silent on community context. Um, but community decision making takes place in the context of relationships with the surrounding lands and waters and air and human communities and plant and animal communities, including decision making about the power plant. So, thinking about some of those connections, the power plant has energy sources. In particular, there's chemical energy in the coal, which comes from the land, and before that, the sun. And there's material sources also. The coal comes from the Powder River Basin in Wyoming. That's where 40% of the coal that's used in the United States comes from. And also, water for the cooling system is drawn from the Ocmulgee River nearby and the Lake Juliet Reservoir near the premises. The plant also has emissions. The energy emissions include electrical energy. That's about a third of the energy that comes out of the plant, and that's transferred to the electrical grid. That's the purpose of the power plant. The power plant also emits thermal energy. That's about two-thirds of its energy is transferred to the lands, waters, and air, meaning it heats them up. There are also material emissions of the power plant. The residue of the burned coal goes into an ash pond on the site, and the exhaust gas goes into the atmosphere. And finally, the warmed water is returned to the river and the reservoir nearby. I want to mention Indigenous presence because Indigenous people face environmental consequences, especially directly, partly due to a close relationship to the land. The Powder River Basin, where the coal comes from, is the traditional land of the Cheyenne, the Crow, the Métis, and the Mandan people. And coal mining is the main source of revenue for the Crow tribe, which illustrates the complexity of some of these relationships. Plant Sharer, meanwhile, sits on the ancestral lands of the Muskogee people. Indigenous people were driven out of Georgia in the 1830s as part of the Trail of Tears. The federal government recognizes no tribes in Georgia today, but there are at least 150,000 Indigenous people who identify as Muskogee who live in Georgia. I also want to mention the exhaust gas. According to the US Energy Information Administration, Plant Sharer emitted about 7 million tons of carbon dioxide in 2020. Each metric ton of carbon dioxide emitted in 2020 is projected to result in, a small number of excess deaths worldwide between 2020 and 2100. That corresponds to about 1,560 excess deaths due to this one power plant. And the causes of those excess deaths are ambient heat, atmospheric changes, disease patterns, flooding, and effects on the food supply. So to place plant share in its community context would be to kind of add to this original diagram the exhaust gas, the coal in the Powder River Basin, and the Ocmulgee River as examples of the contexts that are affected by this power plant. The community decision making about this and every power plant is continuous. So every time I speak about it, I look up the latest news on the power plant that I'm talking about. And here's what I found recently. There's a discussion about whether this plant should be closed. They were planning to close it, but then decided to extend the life of the plant because of demands due to data center energies. Sorry, the energy demands due to data centers. And there's also an ongoing discussion about what to do with the waste from this plant. I remember I said that the coal that's burned goes into the residue goes into an ash pond on the premises, and this ash is toxic and leaches into the groundwater. So here's a recent article saying that there's been legal fights over the coal ash and they've resolved that, but there's ongoing questions about how they're disposing of the toxic waste. And I've been speaking about this particular plant in Georgia because it's, like I say, distinctively large, but power generation is a local issue. So wherever you are, the issues are specific to your area. So on the left, I'm showing a diagram of how Georgia generated electricity in the first 20 years of the 21st century. And as you can see, it had been mostly coal, but in more recent years, there's less coal and more nuclear and natural gas providing the energy to Georgia. Whereas in the state of Washington, where I live, the Washington generates electricity primarily by hydroelectric means and has done so for some time. So near me, the most of my electrical power comes from the Skagit Hydroelectric Project, which is a series of dams. And hydroelectric power is renewable and clean and has flexible power production, which are great features. But it also drastically alters the landscape. It raises the water temperatures and it blocks salmon migration. And these issues are also important for community decision making. Some recent news articles talk about, how difficult it is to obtain fish passage over the dams, which were, supposed to include that when they were built, but didn't always. The negotiations with local indigenous people are ongoing, and there's just a lot of stakeholders between the needs for energy production, the salmon, the farmland, and the people that live in the area. So what I hope I'm illustrating is that physics and society shape each other, that while physics values include university and idealization and independence from human concerns, physics is also connected to community decision making, and it should be. And what I want to offer you is that actually the physics concepts are not neutral to begin with. They are created and sustained by people in specific times and places for reasons. The pictures on the right are some of the books that I've found informative in thinking about these issues. So some things I've learned about the socio-political origins of the energy concept and the physics energy concept in particular. It was shaped in the British Industrial Revolution, and where the sort of problem facing the people of the day was to improve steamships and factories to transport and process goods that were being brought to England from its global empire. So there was a strong priority on heat and work and efficiency. The values informing this scientific advancement were explicitly capitalist and colonialist, and there was no concern at all for renewability, cleanliness, sustainability, and so on, because those weren't the concerns of the time. So, what I want to offer is that we decide how to do science, and we also decide how science should be taught. I want to quote Max Liboiron, who is Métis leader of the Civic Lab for Environmental Action Research, which is an anti-colonial feminist marine science lab in Newfoundland in Canada. They say, every morning when I put on my lab coat, I have decisions to make. How will we do science today? How will we work against scientific premises that separate humans from nature, that envision natural relations as universal, and that assume access to indigenous land? These are not theoretical questions, they're practical questions. Um, However, there's another point of view that science is independent of human values, or should be. I've had papers reviewed in which reviewers made statements such as the following: the concept of energy conservation requires human interaction to recognize it, but the concept itself has no historical or social value other than being determined at a certain time in history. Another reviewer said, there are no human values embedded in energy conservation. The concept of energy conservation, of course, comes from humans, but still, there are no values embedded in it. And a third person said, humans were needed to recognize and study the various patterns and symmetries and to give names to them, but they were there all along. Comments like this raise some big questions, like, are there patterns and symmetries in nature independent of the humans who name them? Must physics concepts be independent of social values to be legitimate? And would scientists with diverse social identities make unique contributions to science, or is science independent of human perspectives? So I'm not going to answer these questions today. They are huge questions, although I do love talking about them. But what I want to say is that no matter what your answers to these questions are, the current energy concept does take a stance on them by being silent on climate concerns and other matters of community decision making. What I want to propose is that we should create an energy concept that's suitable for introductory physics and that includes renewability, sustainability, cleanliness, and whatever other features are essential to climate science or the community decision making that we care about. And I do mean create. There isn't one, as far as I know. We're going to need an expansive we for this project. We're going to need voices represented that are relevant to the community decision making that we're trying to do. And high school physics is especially well suited to this kind of expansive we. High school teachers are extraordinarily creative. High school students represent the diversity of their communities, and high school is local. It's usually administered at the city or county level, so community engagement is really natural and often strongly supported in this context. I want to share with you just a couple examples of some high school teacher partners who are doing amazing work in this area. Nora Paul Schultz in Boston, Massachusetts, is integrating environmental justice issues into her teaching of energy and electricity. And Vicki Augustine is empowering her students to practice participating in public decision making around power use by having mock town halls where they decide about energy matters in their community. So in conclusion, I just want to say that science education should serve community decision making, especially about key climate relevant activities. And we should be creating an energy concept for introductory physics that includes renewability, sustainability, cleanliness, or whatever other features are essential to climate science or the community decision making we care about, and that high school teachers and students might be where the magic is. Thank you so much.